I'm Myung from Seoul National University. In this presentation, I will be talking about hypervisor fuzzing, MundoFuzz. Okay. The hypervisor is the system software that manages and runs virtual machines. The hypervisor allows multiple remote users to rent virtual machines and provide virtualized hardware resources. This is particularly important today because the computing trends are rapidly shifting towards cloud computing. Using the hypervisor, cloud computing platforms can enable flexible resource management on virtualized platforms, which can efficiently service billions of users. However, from the security point of view, the hypervisor introduces a critical attack surfaces that needs careful attention. Let's assume one of the guest VMs is malicious. If this attacker, guest VM, exploits the vulnerability in the hypervisor and gains the hypervisor privilege, then all the guest VMs running on the hypervisor would be compromised as well. One effective way to identify the vulnerabilities is fuzzing. The fuzzing keeps generating random input and providing it into a target software. During the fuzzing, it monitors whether an abnormal behavior like crash occurs. Hypervisor fuzzing would be similar, but the key point is that the input would be provided by the virtual machine. Moreover, yet another important difference is that these inputs are low-level I/O operations using various I/O interfaces, such as PIO, MMIO, DMA, and so on. In order to fuzz the hypervisor, virtual devices will be attacked primarily through the random input. However, hypervisors emulate a lot of virtual devices, and each virtual device has its own unique input format. As you can see here, the hypervisor emulates devices like NVMe, NIC, USB, and so on. Most hypervisor fuzzing techniques rely on two methods to generate the random inputs. The first is to generate random inputs without knowing the input format. And the second is to generate precise input relying on manual input grammars. But all these two have their own problems. First, the random input cannot generate the correct input format, so it fails to explore the deep state of the devices. Second, manual input grammar specification is non-trivial and it is costly. So we wanted to solve these two limitations by fuzzing the hypervisor with the automated grammar inference. MundoFuzz is designed to improve hypervisor fuzzing capability with automatic grammar inference. However, we found two challenges to infer the grammar. This is related to the unique features of the hypervisor. First, the hypervisor grammars have hidden input semantics. Second, the hardware features of the hypervisor introduce coverage noises. So, in order to solve these challenges, we developed an approach called Statistical and Differential learning with coverage. As you can see in the example, the input is presented in a sequence of I/O operations, so it is difficult to infer semantic meaning behind the input. In fact, there are two hidden semantics here. One is I/O address semantics, which assigns meaning to the I/O addresses using different types. So I/O operations show its dedicated behavior through correct I/O address value. There are two types of I/O addresses. For control type, the I/O address value is used as a function number to invoke device function. For data type, the value is used as a data parameter to be used in the invoked function. For example, in the first two I/O operations, we can infer the meaning that it invokes the function called find sector and transfer the data parameter to be used in the find sector. And we can infer the meaning of the last two operations in the same way. So, the other hidden semantic is I/O order semantics, which assigns meaning to an execution order of the I/O operations. So the I/O operations function correctly if they follow the correct order. For example, I/O operations are positioned to perform the device behaviors as shown in blue-colored and red-colored I/O operations. Just as the find sector should be performed before the write data, I/O operations should follow the execution order. Among the two hidden semantics, let me first show how to infer I/O address semantics by identifying I/O address types. The key observation here is that different I/O address types behave differently depending on which values were assigned to it. So we inspect the coverage by writing different values. For the control type, the coverage appears differently depending on the I/O address value. As you can see in the figure, different coverage is captured because the different values were written to the I/O address. So we confirm this is control type. At the high level, these two invoke different functions. On the contrary, for data type, the same coverage appears irrespective to the I/O address value. So we can confirm that it is data type. At the high level, these two invoke the same function, and only the data parameter has changed. Secondly, we identify the execution order to infer I/O order semantics. We observed that I/O operations wouldn't work correctly without the prerequisite I/O operations. So we check whether the coverage is distorted by omitting some I/O operations. For example, for one input, all I/O operations are performed in the correct order. And for the other input, the first two I/O operations are skipped and the last two I/O operations are performed. Then we compare the coverage for the last two I/O operations. And if the coverage is different, we identify that the last two I/O operations are dependent on the first two I/O operations. Yeah, check. While we measure the input coverage for inferring hidden semantics, we found that the measured input coverage includes unwanted coverage. This is because the hypervisor virtualized asynchronous event. The asynchronous event can be a timer or interrupt event. This asynchronous event is performed in the middle of the hypervisor operating on the input, and it introduces a non-deterministic coverage. To make it easy to understand, let's use the previous example. We inspect that only target coverage will be measured. However, during the first execution, you can see noise coverage by an interrupt event. During the second execution, noise coverage occurs through a timer event. Eventually, it is difficult to measure clean target coverage because of the various asynchronous events. To resolve this challenge, we observed the characteristics of target coverage and noise coverage. For target coverage, it is always captured for all execution. On the other hand, for noise coverage, it is captured differently for each execution. Through the observation, we designed a statistical differential coverage measurement that removes noise coverage by intersecting all measured coverage. By doing so, we can secure a clean target coverage. MundoFuzz has the following overall architecture. First, we collect a hypervisor input trace issued by various real-world applications and manipulate the input considering two hidden semantics. Second, we remove noise coverage and obtain clean target coverage through the statistical noise filter. And using the coverage, we analyze the two characteristics of input semantics and create the grammar. Finally, MundoFuzz finds the hypervisor bugs using the grammar. So what did MundoFuzz find? MundoFuzz found new 40 bugs in QEMU and Bhyve. We found 23 bugs in QEMU and 17 bugs in Bhyve. Also, to demonstrate the performance of MundoFuzz, we compared the coverage to the state-of-the-art Hypervisor Fuzzer, Hypercube, and NIX. MundoFuzz outperforms overall performance by 4.9 and 6.6 respectively. We also compared NIX with manual grammar rules to MundoFuzz through the complex USB device, and MundoFuzz shows higher coverage than NIX with manual grammar rule. Now, let me conclude the presentation. I introduced the hypervisor fuzzing technique called MundoFuzz. It statistically removes noise coverage and automatically learns the grammar using two hidden semantics. Also, MundoFuzz discovered 40 new bugs. MundoFuzz also presented better coverage compared to state-of-the-art hypervisor fuzzer. Thank you very much for your attention. I would be very happy to take any question.